according to my YouTube channel. Where are we? Nothing like chemistry, organic chemistry, especially on a Friday afternoon in June. All right, so let's see here. We've got cyclohexene. That's this compound here. It's got 6 carbons. And then we've got a compound with 9 carbons here. And we notice that we're adding those 9 carbons through a double bond on the ring. And so, you know, what would be a strategy here? Is there any reaction that anybody could think would be a good idea to make this carbon-carbon double bond? Maybe a reaction we saw last class. Oops, there we go. Is there a name reaction that anybody's thinking of to make that carbon-carbon double bond? We talked about making alkenes last week, an alkene carbon-carbon double bond. And for that, we were talking about Wittig chemistry. So we're talking about the Wittig reaction. And I told you that Georg Wittig won the Nobel Prize for that a long time ago, 1979. And what would be the ketone that we would need? We would want to have this ketone, cyclohexanone, and then we would need to have our Wittig reagent. So we have our carbon-carbon double bond, 1, 2, 3. And then we would have our triphenyl, our phosphorus with the 3 phenyl groups bound to it. And this is what we call the ylene form. You could also draw the ylid form like this. Either one is perfectly acceptable. Nothing wrong with either of them. So we're going to assume that we have the Wittig reagent. We're going to assume that we have that. So now the question becomes, how do we get from here to here? How do we get from cyclohexene to cyclohexanone? Does anybody have an idea? Anything that we could try? There's a few things. There's one thing that I would think is better than anything else. There's one reaction I would put at the top. Does anybody have an idea where you would start to go from this compound to cyclohexanone, the alkene to this ketone? We're not adding any carbons. All right, well, if you're unsure, what I think the easiest thing to do would be to just add water to the double bond, right? There's an axis of symmetry or a plane of symmetry here. And therefore, if we just treat this with aqueous acid, that's going to add water across that double bond. And again, since there's symmetry, we don't end up with any chiral centers. There's no Markovnikov or Anti-Markovnikov to worry about. We just end up with cyclohexanol. Now, if we want to take that cyclohexanol and convert it to cyclohexanone, all we have to do is oxidize it. And what are the conditions we could use to oxidize this? I mean, we could literally use the Swern reaction, we could use PCC, or we could use the Des-Martin periodinane, any one of those. And again, the Swern, you need to know the Swern details. The Swern is DMSO and oxalochloride, followed by triethylamine. I'm not going to write those down, but any one of these would work. You could also use the Jones reaction, which is sodium dichromate, sulfuric acid, and water. Those would all be reasonable for this oxidation because you're taking a secondary alcohol and you're converting it to a ketone. And then in the last step, we're going to do our Wittig reaction. So what's our ylid going to look like? It's the one in the box over here. We have our double bond. We have 1, 2, 3 carbons, and then we have our phosphorus with 3 phenyl groups attached to it. And again, the Wittig reaction, I want you to be aware of the mechanism of the Wittig reaction. We went over it last class, how you form the oxyphosphatane via a 2+2 cycloaddition, after which there's a fragmentation that produces the alkene. Plus, you end up with this byproduct, which is TPPO, or triphenylphosphine oxide. So TPPO is this guy, triphenylphosphine oxide, the byproduct of the Wittig reaction. All right, there we have it. Now, normally a stabilized, a small alkyl group is going to give you the Z alkene, but there's no E and Z to worry about in this case, and so we don't even have to take that into consideration. Well, let's move on from there. And I thought next we would try 19. I think I got this question written down incorrectly. Yes, I do. So I wanted to skip ahead. Sorry, I made a mistake on this one. I wanted to try, let me just erase all this. It was question 19.73D. Yeah, 19, let's see here, 19.73D. And the question was, take cyclohexene, the same starting material we had in the previous question, and we want to make a cyanohydrin, okay, where we have a hydroxyl and a nitrile attached to the same carbon. We call that a cyanohydrin, and they're going to come up in chapter 20, the cyanohydrins. And of course, they came up in this chapter, and we said we could take the nitrile and reduce it to a primary amine, or we could hydrolyze it with aqueous acid to a carboxylic acid. That's neither here nor there. We just want to make the cyanohydrin, and what you should remember is that the cyanohydrin must be made from the corresponding ketone, okay? And then our reagents to make the cyanohydrin are going to be potassium cyanide and HCl. So the book kind of gives you a barrage of different ways, or a deluge of different ways to make the cyanohydrin, but this is the preferred way, just potassium cyanide and HCl. So then the question becomes, well, how are we going to get from here to here? Well, we just did that, so let's just go through it very quickly. First, we're going to do the addition of water across the double bond. We make cyclohexanol. We're going to oxidize that. I'm just going to choose the Des-Martin periodinane. Like that, we end up with cyclohexanone, and then we treat that with potassium cyanide and HCl, and we end up with our cyanohydrin. Well, let's try something that involves another functional group, now one that we're going to have to make from a nitrogen nucleophile. So this is E, and the question is, if we started with methyl cyclohexane, this compound here, could we make an imine? And I'll show you where the imine is. It's right over here, right? Could we make an imine like that? And what you would want to remember from our lecture and from the book is that if you want to make an imine that has a hydrogen attached to the nitrogen, then what that's going to come from would be the corresponding ketone. So it would be 1-methylcyclohexanone plus ammonia. Okay, again, if this was an R group, then it would be a primary amine. It would be RNH2, but it's not an R group, so it's not a primary amine. It's just plain old ammonia. Thus, the question becomes, well, how do I get from methyl cyclohexane to cyclohexanone? For my first reaction with my methyl cyclohexane, does anybody have any ideas what would be a good first reaction here?
Bromine with light.
Absolutely. It's the only option, isn't it? Right, Karen? I mean, even if you were stuck on a quiz, God forbid, you know, if anybody ever gets stuck, if you're ever given a hydrocarbon, you've really only got one option, right? So we could take that, put bromine on here. And now if we want to make this ketone, this cyclohexanone, let's do another retrosynthetic step. That's probably going to come from an alcohol, because we have no way to just make a ketone unless we put an alkene in there, and that just seems way too laborious. So that means we're going to need to have this alcohol, and then that would come from this compound where we have, 1-methylcyclohexene, and all we have to do is an anti-Markovnikov addition of water. So then the question becomes, okay, well, how do I get from here to here, right? So there's two types of beta protons, aren't there? There's these ones out here, the red ones, and then there's the blue ones. Now, I want to pull off the blue one to make the double bond here. Could anybody suggest a base that I might want to use to do that? To make the Zaitsev. Sorry, go ahead.
Sodium methoxide.
Yeah, you want to make this. You want to make the Zaitsev alkene, right? So I would buy that sodium methoxide. Sounds perfect to me. That's going to give you the Zaitsev compound. That. Now what do we do? Our anti-Markovnikov addition of water, and I bet you guys have these conditions memorized frontwards and backwards. Borane THF, which is going to show up again in the carboxylic acids chapter, used for a different function than hydroboration oxidation. I'll get into that probably next lecture, so probably on Monday. But we end up with this alcohol, and then all we have to do is convert it to the ketone. For our oxidation, I'm just going to choose PCC so that I can avoid writing too much. And then the last step is going to be formation of the imine. Now, what do we need? We saw that we needed ammonia, So we need ammonia to do that. We also need a catalytic amount of acid. So that's what the H plus in brackets means. The brackets represents a catalytic amount. And then we always write minus water because we want to remove water from our reaction mixture. That's quite a few steps, isn't it? Let's take a look. We got 1, 2, 3, 4, 5, 6. Yeah, I consider 6 to be a lot of steps, you know. And I mean, how are you going to do this? The only way to do this is to really be pretty solid on your chemistry, on knowing what reaction does what. I mean, you could probably guess this one, the first step, and as long as you know what an imine is, you would know this part. But then you kind of have to piece it together, going backwards a little bit. So, there's definitely some synthetic prowess involved in this one. I think that next one is pretty reasonable. So I wanted to take a look at, there's 2 more here that I thought were just dandy, for lack of a better word. There probably is a better word, but I'm lacking it. So let's see, 19.73 G. What if we had, let me see here. I gotta find my textbook. I just want to make sure I have this written down correctly. Yeah, this question. This question is a doozy. I like this one. So you're just starting it with benzene, and then they want you to put this enamine on here. This is one where I think retrosynthesis really comes into its own. My students, right? You have to understand what an enamine is, and you got to be able to recognize that right away. And the first thing that I would do, if I was faced with this problem as a student, is I would do a retrosynthesis. Okay, and I would say the only way that I could make that enamine would be from acetophenone, right? Would be from this compound. And all we have to do is take acetophenone, the compound in red, treat it with dimethylamine, right? Because there's a methyl group here and a methyl group here. So you'd need dimethylamine, catalytic amount of acid, and remove water. So then the question becomes, how do I get from here to here? I can think of a couple of ways, but one way is head and shoulders above all of them. Could anybody tell me a way that they've got? I'm sure you've got better, great answers.
Acylation.
That's the best answer, isn't it, right? A Friedel-Crafts gets it done, it's done like dinner. It's really finished quickly. So what Caitlin is saying, if you had acetyl chloride, this compound here, and aluminum chloride, we know that we can do a Friedel-Crafts acylation on benzene, and we make acetophenone like that. You know what? Okay, let me ask you a tough question. This is not an easy question. Can anybody tell me a much more steppy way of doing this? Is there a long way you could think of to do this? I wouldn't use it. I wouldn't give you, I guess, I wouldn't give full points because it's too long. But there is another way that you could do this based off of what we've learned that I can think of, at least off the top of my head. Did anybody try doing this with a green yard? So what I'm saying is this, like a really long way to acetophenone, we can count the steps, would be to take benzene. So then you brominate it. So we'll put bromine and iron 3 bromide. So then you make this bromobenzene. Then you treat it with magnesium. So that gives you phenyl magnesium bromide. So we have phenyl magnesium bromide like that. Then to add 2 carbons, you could treat it with this compound. This is called acetaldehyde. That's neither here nor there. Followed by aqueous acid. So that would give you the secondary alcohol like this. And then you could oxidize it. Oh boy, this is brutal. PCC. We'll just choose that. Okay. And you could choose anything. And then you'd have acetophenone. I mean, see how powerful organic synthesis can be? One step versus 1, 2, 3, 4, 5, if you could take your pick, I mean, obviously you would go with one step. I mean, life is finite. We don't have the time to be messing around with steps like that. So that gives you an example of something, where you know how to do it. Another way we could, but it's just way too long. I mean, you end up losing material at every point along the synthesis. So I would say not optimal. Optimal. It's like they say, you can drive a car with your feet, but it doesn't make it a good idea. So you could make the compound that way. I wouldn't say it's a good idea. Okay, so now that we have that, we're only one step away from our enamine. We need dimethylamine. And I know we haven't done amine nomenclature, but you can imagine this is dimethylamine, okay? So dimethylamine, a catalytic amount of acid, and then you lose some water, and you make yourself an enamine. Later on, I think I told you this the other day, we're going to talk about how enamines can be used as nucleophiles, but that's another day. Hold on, just let me... Could you start with chlorine and add a bromine later? I'm not sure why you would do, or how you would do that. So how you would replace a chlorine with a bromine exactly. That might be something we could discuss offline. All right. There's another one that, you know, sometimes our author of our textbook, he comes up with these questions that look super intimidating. This is 19.73H. Another one I thought was, well, I don't know how cool it is, but it's interesting to say the least. So you have this compound that has 1, 2, 3, 4, 5, 6, 7 carbons in it. So we've got 7 carbons in here. And then he says that you want to make this compound here. We have an oxygen here. And then you've got your CHEM dimethyl. Oh, and there's these other methyls here. Could anybody tell me, and it's, you know, it's not a trick question, what functional group is in this compound? You're unsure, it's cool, but could anybody identify a functional group in here? It looks like an ether, huh? It does kind of look like an ether, right?
An acetyl?
It's close, yeah. So I wouldn't say it's an acetyl group would be this, right? If you just have that. So it's an acetal. Yeah, and I'm not trying to be a jerk, okay? So
that's what I meant to say.
Yeah. So this isn't an acetyl group. That's right. And if you have a carbon that's got 2 ethers on it like that, yes, it's called an acetal. Yep, good enough. Okay, so we have an acetal on here. So let me just delete this stuff here. So let's do a quick retrosynthesis. Yeah, and we'll draw the alcohol, which is a diol that you would need. So it would have these carbons connected. You'd have a hydroxyl here, methyl, CHEM dimethyl, like that. And then your carbonyl compound would just be formaldehyde. So we can assume that we have formaldehyde. It means only 1 measly carbon in it. But I think hopefully you can see that we're going from, right, you kind of got like 1, 2, 3, 4, 5, and then here you have 1, 2, 3, 4, 5 carbons. That's the way I'm kind of connecting the dots. And so the question becomes, how do I end up reducing this compound in such a way that I end up with a hydroxyl on here, right? That's kind of what I'm thinking. You know, how would you get to there? You know, and if you think about it, you could make that diol, you could make that from this compound. What if you had the dicarbonyl? If you had the dicarbonyl, all you'd have to do is reduce it, use excess lithium aluminum hydride or sodium borohydride. Either one would work. So then hopefully now you can see if we count the carbons again, 1, 2, 3, 4, 5, like that. What we're trying to make on carbons 1 and 2 and 4 and 5 is a methyl ketone. And we learned how to make a methyl ketone from an alkyne way back in chapter 9. If you go back to, I'll just write it here, chapter 9, if you want to go back, this is the Markovnikov addition of water across a triple bond. So we use mercuric sulfate, sulfuric acid, and water. And remember, that gives you an enol, but the enol undergoes tautomerization to give you the methyl ketone. So we end up with this compound where we have the diketone like that. Now we want to reduce that. And we have 2 carbonyls, so you could put excess lithium aluminum hydride, whatever. You know, sodium borohydride doesn't get a lot of love in this course, so let's try that for today. So sodium borohydride, we'll even put it in ethanol as our solvent, and that will give us this, well, what would that be? 3,3-dimethyl 2,4-pentane diol, I guess. Like that. And now we can just build the acetal, right? All we need is formaldehyde and a catalytic amount of acid. You lose some water, and that's it. So, you know, I find this is one of those questions that to me, it looks deceptively complex. You know, you look at this and like, how the hell am I going to get from here to here? Well, you really have to tie, to me, this is kind of the key step. If you have this figured out and you understand the retrosynthesis, and I think my students understand acetals pretty well, you know, then you can kind of piece it together with the reduction and everything. Any questions about that one? I really like that question. I mean, like, what do you mean by like? Well, I just thought it was interesting. Hold on, there's another one I want to look at with you. Just give me a second. I have so many notes. Oh, where was it? Just give me 1 second here. There was a question in the book. I was looking at it 2 days ago, and I thought it was really interesting. Just bear with me for 1 second. It's after the green yard stuff. It's after this. Oh, fiddlesticks! I don't think I can find it. Oh, darn! I thought it was in here. So let me go back here. I might have it mixed up. It might be in the chapter. It might be in the next chapter. I think I'm getting overly excited thinking about chapter 20. Yeah, I think it's a question in chapter 20. All right. Well, let's take a look at another one here. Bear with me. Did that one. Did this one. Did that one. Okay, let's try another one here. Just this one's kind of a quick one, but I thought it was kind of interesting. So this one, if we take an aromatic ring that has an alkyne attached to it. So we've got phenylacetylene like this. Okay, and we want to take it, and we want to make this alcohol. So we want to make a primary alcohol off of those two carbons, and we're actually adding a carbon in the process. So I think that anything where you're adding a carbon, right? If you count all the carbons over here, you've got 6, 7, 8 carbons, but here you've got 6, 7, 8, 9 carbons. You're adding one measly carbon here. And notice that you're making a primary alcohol, right? A primary alcohol. Did anybody try this problem, or could anybody tell me if they have any retrosynthesis ideas, or where you might have, how you might have made this primary alcohol, from where, from what? You know, what would be a good precursor to this one? Do you have an idea about that? Okay. All right. What I was thinking is you could make a primary alcohol. I mean, there's not many ways to make a primary alcohol. Really, the only way that I could think of doing this is if you have a double bond here, right? If you have a double bond on here, then you could do an anti-Markovnikov addition of water. So then the question becomes, well, how the heck would you get from here to here? You added an extra carbon. There's no way you can add a green yard to this. It won't work. That's impossible. So then that requires us to do one more retrosynthesis step. And I know you're still studying for the quizzes and everything, so I don't expect you to know the answer to everything right this minute. But here's what I consider to be the key step. I mean, primary alcohol, again, not many ways to make a primary alcohol. accept an anti-Markovnikov addition across an alkene. And so we're making a carbon-carbon double bond. So I think the best way to do that would be from acetophenone and then to use a Grignard reagent, right? Use a Grignard. So we would have CH2, and then we would have our PPH3 over here like this. I think that is probably the best way to make this compound, right? Because this is the ylene form. But if you draw the ylide form, so we have the negative charge on the carbon, we have the positive charge on the phosphorus, put in my lone pairs here, right? The negative charge on the carbon is going to act as a nucleophile, and we're going to create a bond between the oxygen and the phosphorus to make the oxophosphatane, which can then undergo fragmentation and will produce this carbon-carbon double bond. Thus, the problem becomes, you know, how do I get from here to here? Well, we have already gone over this today, that if you take an alkyne and you treat it with mercuric sulfate, sulfuric acid, and water, we can do a Markovnikov addition of water. And if you've forgotten what an enol is, right, it's just like we add water in the Markovnikov fashion, like this. But this enol undergoes tautomerization, which is just an isomerization that involves the movement of a pi bond and a hydrogen proton, and we end up with this compound. So now we just need to do the Wittig chemistry. So this is our Wittig reaction, very important reaction in organic chemistry. And let's draw the ylene form here, and that's going to give us the compound that we need, like this, where we have our double bond, like that. And now I'm kind of running out of space here, but to do the formation of the primary alcohol, we're going to first treat that with borane and THF, followed by hydrogen peroxide and sodium hydroxide. Those are conditions I guarantee you have memorized by now. I'm sure you could bring those up in your sleep, even if you didn't want to, right? All right. Well, I think that's, oh, just let me check one more thing here. Why don't we try one mechanism question together? And this is kind of a, not an advanced problem, but I think it's one that's a little bit challenging. It's question 19.58. So if you look at the question, it's got a whole bunch of text with it. Question 19.58 says you're starting with this compound. This is called glutyraldehyde. Let me draw it out here. 1, 2, 3, 4, 5 carbons. So we've got glutyraldehyde, and then we're just treating it with H3O plus catalytic amount, okay, and water. And it says it's in equilibrium with this form here. So it's like you've got two hemiacetals. It's like you've got one on this side and you've got one on this side, right? So it's called the cyclic form, and it just says, come up with a mechanism for this. You know, how the heck would this work? What would cause this to happen, okay? And so we've got to find a way to get from here to here. But if we're in a strong acid, I mean, neither of these carbonyls, none of the carbons are adequately electrophilic to react with water, and so they must be protonated first. So let's start with a proton transfer. So we're going to do a proton transfer. We'll write out the structure. Oops, please tell me that didn't delete it. Good. And we'll write out the structure of hydronium like this. We'll do a proton transfer. You could do it to either side. It doesn't matter. You're still going to get the same answer. And now we've got an oxonium, which is super powerful electrophile. 1, 2, 3, 4, 5. And now water can come in as a nucleophile, and it's going to attack the electrophilic carbon. So let's draw that. Let me just try to not take up too much space. So I'll just draw my water molecule like this. Water is going to attack that electrophilic center. And let's draw what we get from that. So we're going to end up with something that looks, oops. Going to end up with something that looks like this, where we have this hydroxyl. 1, 2, 3, 4, 5. So we'll just draw this like this. And then here's my oxonium, like this. Okay, there's my oxonium. All right. Well, in order for one of those alcohols to make a ring, and this isn't an alcohol yet, it's an oxonium, I'm going to have to do a proton transfer to render them both neutral. Okay, because there's no reason why this is going to act as a nucleophile there, because then I end up with something that's neutral. I want to have everything, all my intermediates having a positive charge. And so the next thing I'll do is a proton transfer. So my water molecule is going to rip off that proton like this. Okay, there we go. And I end up with this intermediate. So 1, 2, 3, 4, 5. Like this. So there's my carbonyl. And now I've got these two hydroxyls, and this is what's going to enable me to make a six-membered ring. Right, if I count 1, 2, 3, 4, 5, 6, now I can get a nucleophilic attack by one of those hydroxyls on the carbonyl oxygen after it gets protonated. So the first thing I need to do is activate it, the proton transfer. So we'll draw another molecule of hydronium. Here we have our proton transfer, like that. So let's see, 1, 2, 3, 4, 5, like that. Now this is protonated. It is a super powerful electrophile now. I can draw both of these hydroxyls, put in some lone pairs here, and now this is going to act as a nucleophile, and the carbonyl that was protonated will act as an electrophile, and that makes my six-membered ring. You can look at my numbers before. We can write them here. 1, 2, 3, 4, 5, 6. So what if I got? What I'm going to end up with is something that looks like this. I'm going to have my oxygen. Then I've got 1, 2, 3, 4, 5, 6. It's going to have a hydrogen on it, and I'm going to have a hydroxyl here and a hydroxyl over here. And what did we form in this step? We formed water. We have our acid catalyst. It's got to be regenerated. And so what's going to happen is the water is going to come along and it's going to rip off that proton like this. And I end up forming that cyclic compound. Come on, there we go. 1, 2. Not my best drawing, but it will suffice. So all these reactions, acetal formation, acetal hydrolysis, all you have to do is look at where you're trying to get to. You know, what are we doing? You can see that we're obviously adding an oxygen to the molecule. Therefore, we need to add a water molecule. And we want to make sure that our conditions are consistent with the conditions, or sorry, we want to make sure our mechanism is consistent with the conditions, which are acidic. So you want to be sure that you have acidic conditions. If any of you have ever looked at the ACS study guide, whether it's the old one or the new one, doesn't matter. Or if you've even looked at MCAT materials or anything like that, you'll see they love to ask questions about mechanisms in these multiple choice exams, just like I do, where you're not even drawing the curved arrows, but you've got to recognize, you know, which one of these is reasonable. Do I know what a proper nucleophilic attack or loss of leaving group or proton transfer, etc.? Do I know what those things look like? So you need to train your eye to recognize mechanisms. All right, and I can tell you right now that acetal formation and acetal hydrolysis are very important for any kind of standardized exam. And let me just put this bug in your ear. I'm really kind of getting ahead of the game here. But in chapter 20, so I'm still recording this and I'll just tell you. In chapter 20, we learned a couple of major mechanisms that just show up in every exam that involves organic chemistry too. And that is esterification. So I'll just throw these words out to you now, esterification. And then we also learn the hydrolysis of an ester. So hydrolysis of an ester. So that's just breaking an ester apart. Oops. An ester apart. It can be done two ways. It can be done in acid or it can be done in base. And when you hydrolyze an ester in acid, you just call it the acid hydrolysis of an ester. But when you do it in base, it's got a special name. It's called saponification. Saponification. And again, this is stuff that we're going to cover in the next chapter, but I just want to throw those words out to you so that you're on the lookout for them when you're reading the textbook or when you're doing your practice. Any kind of standardized exam, if anybody here is thinking about medical school or dental school, I can guarantee you almost, 90% certainty that they're going to ask you something about these reactions. They're so important in organic chemistry. And of course, I'm going to go over them with you in detail in chapter 20. There we go.